Assalamu alaikum students. Our learning objectives in this class are: what is binary phase diagram or binary isomorphous system, calculate composition of phases using tie line and lever rule, which is previously discussed. What is the microstructure and how the microstructure is developed while we at different composition and we cool down at different phases and at different compositions, and what is the effect on of the composition on the mechanical properties on the different alloys, and we will solve some numerical problems to calculate the composition at mixed phase regions, and we will be able to identify between the different phases, and we will be able to calculate the composition of phases at different temperatures after this class. Assalamu alaikum. Previously we were discussing about the lever rule and the tie line and the lever rule. So in this slide we want to explain it further, that how can we find out the composition of each phase between the tie line. Attached are the two examples of the copper nickel system, and given we want to find out the composition of the element different phases at the given lines. We want to know about one rule. Rule 2: if we know temperature and composition, if we know temperature and composition in one phase diagram, then we know the composition of each phase. If we know temperature and composition, then we know the composition of each phase. The examples are: at TA the temperature is 1320 degrees centigrade. At TA, this is TA, the temperature is at point A. 3 points are given: A, B and D. Point A and point B and point D. At TA the temperature is 1320 degrees centigrade. Only liquid phase is present at this point. Cl is equal to CO, the amount of liquid which is also represented by the CO composition. This is equal to 35% by weight of nickel. 35% by weight of nickel. This is CO. At point at TD, TD is equal to, at point D the temperature is 1190 degrees centigrade, which is known. Suppose if any number of points are given in one phase diagram, if the temperature curve is known, if the vertical point and the temperatures at vertical line are mentioned, then we can find out the temperature. Similarly, at TD 1190 degrees centigrade, only solid alpha phase is present at point D. Ca is equal to CO is 35% by weight of nickel. C alpha composition at solid phase, because over here at point D this region is alpha solid phase, so composition of alpha, which is also known CO, 35% by weight of nickel. At TB at point B, this is if we compare point B with A and D, at point A it's a pure liquidous point. Point D, pure solidus point. Point A is represented by Cl, composition of liquid. Why? Because it's a pure liquid region. Point D will be represented by C alpha, composition of solid region. While point B, it's a bit complex because it's a mixture of L plus alpha. So it's a mixture of liquid and solid phase. So both alpha and L are present. Cl will be equal to C liquid point, which is equal to 32% by weight of nickel. Why we will use the lever rule? If there is a mixture within the boundary of L plus alpha or a mixture of two phases, we will project a line, a horizontal line, which will which will touch the two boundaries, the liquid is and solid. So according to lever rule, at point B the line is projected from the liquid phase to solid phase boundary. Now, in order to find out the composition exactly of amount of liquid and amount of solid at point B, we project this. So we get 2 points. We draw vertical line. 2 points. One meets at the CL because it crosses the it touches the boundary of the liquid phase. So we can get CL, which is equal to 32% by weight of the nickel. The other boundary, which is the solid curve, it touches C. Phase diagrams, weight friction of phases. Rule 3: if we know about temperature and composition, then we know the amount of each phase given in weight percent. The example is also given for point B. At point B, we have 3 points. We are given 3 points. One is A, one is B, and one is D. We want to find out the composition of each phase. For point A, we have previously explained the amount of liquid phase, the amount of liquid at point A. Directly draw a line below the A, that will be CL. CL will be equal to the direct composition, which is known, which is 32% by weight of nickel. Similarly, for point D, it is C alpha. It is also 32% by weight of nickel at solid boundary at this temperature at point TD. The known are CO is 35% by weight of nickel over here, 35%. Sorry, this amount is 35%. Draw a tie line. A tie line is this one, and draw vertical lines. Vertical line CL is 32, C alpha is 43. Amount of liquid CL will be equal to this composition. Similarly, C amount of D, amount of solid at point D will also be equal to this percentage. But now we are interested to find out CL and C alpha for point B. For this, we draw a lever rule, draw vertical points. This is the generalized procedure. Draw vertical points and find out the composite. Write the data CL. This point is CL and this point is C alpha. C alpha is 43. CL is 32% by weight. Weight of the liquid is 100% at point A. At point A, the weight of the liquid is 100% and W alpha is 0. Similarly, at point D, only solid alpha is present, so weight of the liquid at this point is 0, but weight of the alpha is 100%. by weight over here. So we can find out the exact composition of the weight of the liquid solid over here will be at this temperature. Tt will be this one, but now we want to find out Tb, both alpha and L are known. So write out the formula. Wl will be equal to C alpha minus Co divided by C alpha minus Cl, or you can implement the previously discussed formula for the lever rule, which is explained. So the point will be mentioned over here like OMP. So this data is known. C alpha is known, which is 43. C alpha is this one, Cl is this one, Co is the composition, this is the Co, just directly below the point B is Co. So you will come to know that 73% by weight of liquid is present at this point B, and W alpha is, you put the values in this equation, you will get 27% by weight of liquid, by weight of solid. So this lever rule is further explained. This figure is taken from the Celestial book, chapter 9, which is 9.3b. The tie line, this is the tie line, which is a horizontal line drawn from which touches the two boundaries. So liquid is curved and the solid is curved. Consider again the example shown in this figure, in which at temperature 1250 degrees centigrade, both alpha and liquid phases are present for a 35% weight of nickel and 65% weight of copper alloy. The problem is to compute the fraction of each alpha and liquid phases at point B. The overall alloy composition at B is Co. The overall composition of this alloy at B is Co. Co is known. Just draw a horizontal line, a vertical line, you will come about the value Co. Sorry. Weight friction for liquid, which is Wl, which is Cl. Wl we can also represent by Wl, or weight friction, W for weight, or Cl, composition of L. Similarly, weight friction for solid, W alpha, solid is alpha, and weight C alpha. From the lever rule for L liquid phase, the formula is W divided by S. W is equal to S divided by R plus S. The lever rule, S is the line segment from point B to CO, while R is the line segment from the boundary of the liquid phase to point B, the horizontal line. So, or this can further be explained by the formula C alpha minus CO divided by C alpha minus CL. Similarly, weight of the solid phase, which is W alpha, which is equal to R divided by R plus S. Similarly, the example of OMP, a lever line, M was here, O was here, and P was here. OP, MP divided by OP. If you if you are facing difficulty to use this formula CO minus CL, then you can use another formula of the lever rule, which is explained in the previous slide, for the points OMP. So you just put the values of CO, C alpha and Cl. You will come to know about the weight of the liquid and weight of the solid at point B in percentage. Uh, in this problem, you have to calculate the percentage compositions using lever rule. Calculate the amount of liquid at 1 to 50 degrees centigrade in the copper 40% nickel alloy shown in the figure. So the 40% alloy in this problem is mentioned over here. Just draw a perpendicular. This we can use a tie line as has already been drawn, which intersects the liquidus and solidus line. So just below the intersection draw perpendicular. Perpendiculars are already drawn, like for the liquidus phase the alpha the C of L is known. C of L is known, which is 32, and C of alpha is also known, which is 45. C of alpha is also known, which is 45. C of O, that one the known composition is CO. So all of these are given. You have to find out, calculate the amounts of liquid, of solid and liquid. You have to amount of alpha and liquid. You have to calculate the amount of solid and liquid. So in the weight of the solid and weight of the liquid are W alpha and WL. You have to find out W alpha and WL. These are the unknown. So find out W alpha with from the lever rule formula. It's your choice whether you want to use the formula of OMP lever rule, or you want to find out the formula for the lever rule for C alpha minus C O divided by C alpha minus CL, or CO minus CL divided by C alpha minus CL multiplied by 100. It's your choice. Just two formulas are used, so you have to calculate the amount of solid and liquid at this point at 40% Li. Problem number 2. In this problem, you have to determine the degrees of freedom in a copper nickel alloy. Same figure in the same plot. Determine the degrees of freedom in copper nickel alloy at 1300 degrees centigrade, at 1250, and at 1200 degrees centigrade. How can we determine the degrees of freedom if a plot is given, if temperature and composition are known? So for this we have discussed the Gibbs phase rule. You just apply the Gibbs phase rule. Normally the pressure, atmospheric pressure, 1 atmospheric pressure is known for calculation of Gibbs phase rule. So at each temperature, draw a horizontal line and then a vertical line in order to know about the number of phases that you have to pass through, how many phases, and then later on you put that phases in your equation for the Gibbs phase rule, which is very easy. And then from part B, 1250, again draw a horizontal line from the temperature line towards the liquidus solidus curve, and then draw a perpendicular and repeat the same procedure for 12. Concept check. A copper nickel alloy of composition 70% by weight nickel and 30% by weight copper is slowly heated from a temperature of 1300 degrees centigrade. At what temperature does the first liquid phase form? What is the composition of the liquid phase? And at what temperature does complete melting of the alloy occur? what is the composition of the lost solid remaining prior to complete melting? The answer may be found out at this website, which is mentioned by Celester. You can find out the answer. This is your home assignment. Another concept check. Is it possible to have a copper nickel alloy that at equilibrium consists of an alpha phase of composition 37% by weight of nickel and 63% by weight of copper, and also a liquid phase of composition 20% by weight of nickel and 80% by weight of 80% by weight of copper? If so, what will be the approximate temperature of the alloy? If this is not possible, explain why. The students can find out the answer by visiting this website written by the Celester. So this is here is an assignment problem. Students will solve this by themselves. Determine the composition of each phase in a copper 40% nickel alloy at 1300 degrees centigrade, 1 to 7 degrees centigrade, 1 to 50 and 1200 degrees centigrade. Calculate the amount of L. Determine the composition of each phase of copper. You see this red line, this vertical, at this point, at this vertical red line, the overall composition is 40% by weight. We have several temperature points. One is 1300 degrees centigrade. So just draw a horizontal line from 1300 degrees centigrade. This is point 1. You will know about the phase. Over here, this is complete 100% liquid solution because it has crossed the boundary of the liquidus line. So you will get a complete composition at this point at 1300 degrees centigrade, which is Cl. Amount of Cl will be equal to 40% by weight. So this is one answer. The other answer, what will be the composition at 1 to 70? 1 to 70 is between the temperature lines 1200 degrees centigrade and 1300 degrees centigrade, which is slightly above. This is the point B. So over here you will use the lever rule. You will use the lever rule. Just follow the same procedure which is explained in the previous slide. Draw a horizontal line. From that horizontal, which touches the boundaries of the liquidus and solidus line, draw vertical lines from which is drawn over here as well. Find out the composition below the those vertical points. One will be Cl, which is crossing the liquidus line. The other will be C alpha, which crosses the solidus line. And now find out the Wl and W alpha. That will be the composition at 1 to 70 degrees centigrade. Now 1 to 50, you just it's your assignment to calculate the exact amount using your calculator. The third one is calculate the composition at 1 to 50. 1 to 50 is also above between the 1200 and 1300 degrees centigrade. So it's also it may be the mixture between the alpha plus L region. So it's your assignment to find out the exact calculation. The third question is to find out the temperature at this liquid line to a 1200 degrees centigrade. 1200, just draw a horizontal line from 1200 degrees centigrade which touches the same. Now you are lucky, you can find out the answer very easily. The amount of solid phase is reached, the boundary of the solid line is crossed. So this is C alpha. C alpha at 1200 degrees centigrade. You found the answer very easily for 1200 degrees centigrade, for the 1300 degrees centigrade, but you need to do calculations for the 1270 degrees centigrade and 1250 degrees centigrade. It's your assignment. Rewrite this question and just solve the assignment and submit it to your development of microstructure in isomorphous alloy. The example is equilibrium cooling of a copper nickel alloy. In alloy will be we will study the microstructures development from the cooling down of this copper nickel alloy from 1300 degrees centigrade to at given points A, B, C to D. If we look at these points, A is a 100% liquid phase, while B is entered, B has crossed the boundary of the liquidus line, C is completely in between the regions, D has also crossed the solidus curve at this point. So these are the mixed conditions of the. So we will explain the tie line over here, because we have two types of compositions in the middle of these regions. To compute the equilibrium concentration of these two phases at point B, C and D, the procedure which is used for the tie line, a tie line will be constructed, a horizontal line across the two phases region at the temperature of the alloy. The intersections of the tie line and the phase boundaries on either sides will be noted. Perpendiculars will be dropped from these intersections to the horizontal composition axis, from which composition of each of the respective phase is reached. At point A, it is 100% liquid, and if we study the microstructure, and the temperature is 1300, at this position the solution is in melting stage, and it is 100% liquid solution. But if we look at the microstructure of the microstructure of the liquid phase at point A, but if the cooling begins, no structural changes occurs until point B is reached. So within this region, the microstructure within this region, microstructure will be uniform for the liquid phase. As soon the point B, which is reached, which is the temperature at point B is approximately 1260 degrees centigrade. At this point, the first solid solution alpha begins. At this point, at point B, the first solid solution alpha begins to form, which is a composition dictated by the tie line drawn at this temperature. This tie line between 35 to 36 composition. The composition at this point is 35 over here, and 46. A tie line and the lever rule is drawn over here at this position, 35 to 36% over here. The composition of the liquid is still approximately 35% by weight of nickel and 65% by weight of the copper, which is different from that of the solid solution. With the continued cooling, now if we study the microstructure, over here some small solid particles, these small solid particles which at the percentage of liquid 35% weight of nickel or 45% weight of the nickel begins to form. So this is the microstructure at point B. With the continued cooling, both compositions and relative amounts of each
of the phases will change. The composition of the liquid and alpha phase will follow the liquid S line and solid S line respectively. Furthermore, the friction of the alpha phase will increase with the continued cooling. Note that the overall Li composition, which is 35% by weight of nickel and 65% by weight of the copper, remains unchanged during the cooling, even though there is the redistribution of the copper and nickel between the phases. At 12 to 50 point C. So if we cool down further at point C, again a lever rule is drawn. The composition is slightly changed from 35% to 32% by weight, 32% by weight. And similarly, if we draw a perpendicular line over here, we can reach the 43% by weight of nickel. So at this point, the solidification process is virtually completed at about 1 to 20 degrees centigrade point D. The solidification process is still in process, but until the point D is reached, the temperature over here is 1 to 20 degrees centigrade, and the composition, if we look at the composition, 24%, and we will get the 36% the other solution. So at this point, the solid alpha is approximately 35. The solidification process is virtually completed. If the grains are at point C are slightly developed further, and at point D, the solidification, most of the solid grain boundaries with minute amount of liquid is formed over here. Liquid is 24% by weight of nickel, solidification is 36% by weight of the nickel is formed at point D, and the solidification process is now complete, is virtually complete. Now if we cross the boundary of the solid line, now we reached at point D. If we further cool it down to point E, the solidification process is already changed. No microstructural change, further microstructural change will occur at point E. At point E, the temperature is noted over here, and the composition is 35% by weight of nickel. At this point, we come across the completely solid solution with no amount of liquid, with 0% amount of the liquid in this region. So this is the microstructural study of cooling of copper nickel alloy from 1300 degrees centigrade. So the final solution is polycrystalline alpha phase solid solution that has IUD 35% weight nickel, 65% weight of copper composition. Subsequent cooling will produce no microstructural or compositional alternation, because once the solid S line is crossed, after that no microstructural changes can be seen. Similarly, we can study the behavior of the liquid S line. Above the liquid S line, no microstructural changes will occur. The solution will be 100% liquid with 0% weight of the development of microstructure during non-equilibrium cooling. We will discuss the same Li for the non-equilibrium cooling. For the 35% weight of nickel and 65% weight of the copper Li. So during non-uniform distribution of elements within the grain, segregation occurs. Similarly, if the Li is reheated, the boundaries are weaker or of the weaker grain. Let us begin cooling from a temperature about 1300 degrees centigrade, which is point A prime. The solution is 100% liquid, 1300 degrees centigrade. The microstructure is 100% liquid at 35% nickel Li. The liquid has a composition of 35% weight of nickel and 65% weight of copper at this point. And no changes occur while cooling through the phase boundary, liquid phase boundary, which means that at point B prime. At point B prime, which is approximately 1260, as we have previously explained in the equilibrium cooling, alpha phase particles begin to form, which form the tie line constructed, have a composition of about 46% weight of nickel, 45% weight of the copper. At this point, the tie line is constructed, and according to lever rule, the compositions can be calculated. But over here, small alpha grain particles begins to form. Upon further cooling to point C prime, from B prime, upon further cooling to point C prime, a tie line is constructed. At this point, the composition is 25% nickel, and at the boundary of the liquidus line, and 42% nickel at 40% nickel at the boundary of the solidus line. The liquid composition now has shifted to 29% at point C, to the 29% weight of the nickel and 71% weight of the copper, because 100 minus 29 is 71. Furthermore, at this temperature, the composition of the alpha phase that solidified is 40% weight nickel, 60% weight of the copper. However, because diffusion in solid alpha phase is relatively slow, the alpha phase that formed at point B prime has not changed composition appreciably. That is, the still about 46% weight of the nickel, and the composition of the alpha grains has continuously changed with the radial position from 46% weight of nickel at grain centers to 40% weight of the nickel. The small dash line represents the further diffusion. So further time is required for the cooling. The average composition of the solid alpha grains that have formed would have some volume weight average composition lying between 46 and 40% weight of the nickel, 46 and 40% weight of the nickel, which is discussed between the continuous solid line and the dashed solid line, 46% and 42% nickel. Let's take the average composition to be 42% weight nickel and 58% weight of the copper. We would also find out that on the basis of lever rule compositions, a greater proportion of the liquid is present for those non-equilibrium conditions than for the equilibrium cooling. For the average composition, suppose if we study the grain body, the grains are started forming in the transition stage from the the solid 40% nickel to 46% nickel at C prime. Now, as soon this will continuously begin, the diffusion occurs very slow process at point D prime. The solid grains begins to form from 35% weight of nickel to 40, then 46% weight of the nickel. The grain bodies are started forming. If further cooling starts from point D prime to point E or F prime, over here the procedure a sudden loss in mechanical integrity due to a thin liquid film that separates the grains. A thin liquid film is, over here is formed, which is surrounded by the black line. It is some this produce a sudden loss of in mechanical integrity due to a thin liquid film that separates the grains. Furthermore, this melting alloy coring may be eliminated by homogenization heat treatment carried out at a temperature below the solidus point for a particular alloy composition. During this process, the atomic diffusion occurs, which produce compositionally homogeneous grains. Chord versus equilibrium phases. Composition of solid grains, particles or crystals in the below the solidus line changes as it solidifies. In case of copper nickel non-equilibrium case, first alpha to solidify is C alpha 46% weight of nickel. Last alpha to solidify has C alpha 35% weight of nickel. So here we discuss two terminologies: chord versus equilibrium phases. In case of non-equilibrium cooling, the center of each grain, which is the first part to freeze, is rich in the high melting element, for example nickel for this copper nickel system, whereas the concentration for the low melting element increases with the position from this region to the grain boundary. This is termed as a chord structure, which gives rise to less than the optimal properties. For the fast cooling, we come across the chord structure. For the slow rate of cooling, we come across the equilibrium structure. For the chord structure, first alpha to solidify at 46% weight of the nickel, surrounded by some grains over here. This is non-equilibrium region. Last alpha to solidify is less than 35% of the weight. For a slow cooling rate, the uniform composition of grains of the uniform composition occurs at 35% weight of the nickel, while for the fast cooling the solidification occurs the first solidification occurs at 46% weight of the nickel. So if we look at the grain boundaries surrounded by some particles of the liquid, is this one the microstructure. So if for slow cooling rate, if we magnify the solid grain boundaries of the alpha particle, so this will be a completely solid grain without some surrounding particles, liquid particles. Coring can be eliminated by means of homogenization heat treatment carried out at temperatures below the alloy solidus. During the process, atomic diffusion produces grains that are mechanical properties of copper nickel system. Over here we study the two plots for tensile strength versus ductility or elongation. For the copper nickel system, is we add further nickel to the alloy by composition. We studied the mechanical behavior is change. In the first plot, the tensile strength versus composition is plotted, while in the second one, elongation versus composition of weight percent of the nickel is plotted. The tensile strength increases linearly from about 200 megapascal until the 400 megapascal the peak is reached, but after further addition of the nickel alloy beyond 60, the strength decreases similarly inversely, so that we can reach the pure nickel 100% nickel plot at this point.
the this which is about 350 megapascal. So if we add the nickel alloy to 60%, we can get the maximum tensile strength. Similarly, for the ductility decreases, the elongation decreases from 55% to minimum 30% at the same point or the same composition. The ductility decreases, the elongation decreases, while the tensile strength increases when we further add